Charles is a professor of journalism at NYU, and he writes about physics and mathematics. He has 5 award-winning books. I've read 2 of them, so that I have 3 more I need to go, and I think a new one that he'll tell us about today. But he also writes for a number of publications that are very important, including Science and things that you recognize there that I think some of you also provide information for. He has degrees in mathematics, advanced degrees in mathematics and journalism from Princeton, Yale, and Columbia. And he resides in New York, and he got here last night after all the trials and tribulations, so we greatly appreciate his persistence, and I'll turn this over to Charles to finish the session.
Advances it for you.
Okay, great. Thank you. Hi, everyone. My name is Charles Seife, and I'm a science journalist by trade, which means that I have a slightly different perspective than you guys do. I've noticed as a science journalist that scientists who are embedded in the day-to-day operations of their everyday research often can't take an objective look at the importance of what they do. Most of the time, this means inflated egos. But sometimes, scientists are doing things that are revolutionary, that their work is changing the world and society in a way that they don't notice. And computing on the scale that all of you are doing is revolutionary. And I don't mean this in the Kuhnian paradigm shift sense. I mean this in a societal tectonic shift sense. Big data and big computing are completely transforming society. The change that we're all undergoing is as important in its way as the advent of writing. But as with any revolution, there are bodies. And today I want to talk about this a little bit. And that means that I have to go back to the very beginning. This is a tablet of cuneiform writing. It's actually an account of grain rations that was found a number of years ago. It was dated between 3200 and 3000 BC, found in modern-day Iraq. And it's amazing, if you think about it, that we can look back 5,000 years and figure out how much grain someone had in their storehouse. Writing, the advent of writing, was literally the beginning of history. Before we were able to set down words and ideas in clay or paper or stone, we were stuck with memories that only lasted a few generations, that were passed down orally or through griots. And these memories, these ideas were necessarily distorted over time. Soon, an idea before writing, passed down from generation to generation, becomes an atavistic memory, almost like a dimly remembered dream. But once you had mechanisms for writing, minute details, stuff that no one cares about today, like how much grain Uruk III had in his storehouse, can survive generation after generation after generation. If you think about it, someone like Homer, before writing was really spread very far in Greece, was semi-mythical. Just a few generations later, someone like Thucydides, we know great details about his life and what he did and where he wound up. So in some sense, writing is a revolution in persistence. When we changed media from our brains to something external, to stone, to clay, to paper, ideas all of a sudden could survive long, long after the people who had those ideas died. That the medium of a brain will dissipate rapidly. When we figured out how to get our ideas out of the brain into a more persistent medium, things changed tremendously. The next big revolution I like to talk about is the printing press with movable type. And this is an image of the Gutenberg Bible. To be fair, Gutenberg was not the first with movable type. In fact, the printing press with movable type had been invented several centuries earlier in the East in China. But whoever invented it, the spread of it changed society tremendously. Before, when you wanted to set down an idea, you had to do it with great labor by hand, either chipping away at a stone or inscribing things in your clay or writing. A scribe would have to do it. And if you've ever looked at ancient manuscripts, you know that they're extremely rare, that often really important works only survive in a single copy, like Beowulf. For example, there's only one copy that's extant, and it was actually partially destroyed in a fire. And this brings up the point that single copies or small numbers of copies that survive over time, even though the medium they exist in is persistent, they can still be destroyed either by will or by accident. Throughout ancient Egypt, you have stories of previous monarchs trying to obliterate the memory of their predecessors by chipping off all the inscriptions off of the monuments. Angry rulers can destroy memory. Fire can destroy memory. Monks would often accidentally wipe out important works, like one of Archimedes' work was a palimpsest. It was discovered that a monk had to save the problem of creating a new vellum, a new parchment for writing upon, scraped off an Archimedean manuscript so he could reuse it. And we only rediscovered the palimpsest through modern imaging techniques using electron microscopy and other imaging techniques to find out the writing underneath. So even though writing created persistence for our ideas, it really is printing and mass production of ideas that allowed these ideas to survive with any consistency whatsoever. That once you are able to produce multiple identical copies of an idea, all of a sudden you can replicate them and distribute them widely. And even if the individual copies are more fragile, the ideas themselves are more likely to survive. So printing was a revolution in replication. And this also helped distribution. That is much easier if you print 1,000 copies of something or 10,000 copies of something to get that idea distributed widely rather than having to rely upon carving a couple of tablets or having monks copy manuscripts by hand. But even with the printing press, information could only go as fast as a human could travel. Information was carried on our back. It could go as fast as a horse or as a ship, and that was its inherent limit. That changed in the 19th century when we figured out how to take our messages and our ideas and inscribe them in electromagnetic signals. Whether it's over wires, like the telegraph or the telephone, or wirelessly via Marconi's wireless device or its successors, suddenly information could travel at the speed of light. And we can't improve on that, as you all know. And suddenly, we were able to broadcast in the truest sense. You could send a message into the ether, and in theory, anyone within range could receive a copy. No longer were we bound to a finite copying replication process. Figuring out how to transmit information through electronic media, through electronic signals, was a revolution in transmissibility. And then came the next revolution. That's ENIAC. The digital revolution is every bit as important as the others, but it took longer to take hold. Digital information is actually more than a millennium old. The earliest I can trace it back to is around the 9th century. Three brothers, known as the Ibn Musa brothers, designed a very clever musical device. It was powered by water. And there aren't a whole lot of details about how it worked. But reportedly, the way these devices worked was that the tunes were stored on cylinders, and they were interchangeable. You take one cylinder out, it plays one tune, you put another one in, it plays a different tune. And so the best guess is it's probably not so dissimilar from this sort of device, which is a music box. And if you think about it, a music box really is a digital information storage and transmission device. And what's interesting to me is that the first uses of digital information weren't really revolutionary in terms of storage of ideas, but instead they were really used for trying out baby steps in automation. You've all probably heard of the Jacquard loom. These punch card slat-like devices told the loom exactly what pattern to weave at what time. It was an extremely clever device. But really, the digital revolution got underway when you had memory that was readable and writable electronically. This is probably before all of our time now. That's where we get our core dump from. And once you get electronic magnetic readable memory, it unlocks all of the properties that makes digital information so powerful. Storage in memory is persistent. And because of error correction and distribution, it can, in theory, be even more permanent than stone. Of course, you have to keep your standards from drifting and be able to read something that someone 20 years ago wrote. But the theory is this can be incredibly persistent. If you thought Gutenberg made it easy to replicate, of course, the digital computer leaves it in the dust, and with perfect fidelity. The transmissibility at the speed of light to anyone with any sort of digital device. It beats even radio in that sense. You don't have to have a specialized receiver as much as a universal computer. And what's novel is it's inherently friendly to automation. You can use digital information for automating processes without any problem whatsoever, but it's also very amenable, not just to the gathering, not just to the automation of external processes, but it can automate gathering and processing of data and information. And another revolutionary aspect is that digital information is trivial to store. Your memory is miniaturized, it's cheaper and cheaper by the day. And this last point is as important as all the other points we've been talking about. Just as we've seen a Moore's law change in the processing of information, we've seen a similar exponential growth in memory and storage. And forgive me for personalizing this a little bit, but I've spent much of my life working on computers, not like you guys, but in my own previous incarnation as a mathematician. And I had a knack for crashing every single platform I possibly could. I'd get my hands on a computer, it would crash. And many of my crashes were related to memory. And my first memory of crashing a computer was when I was at the tender age of 7, and I got my hands on one of these guys, a TRS-80, and it had 4K of RAM. And what was miraculous is you could actually store programs on an external device, and the TRS-80s initially came with a cassette drive. The Model 2 actually had a floppy drive, one of these large 8 3/4-inch floppies, which probably half of you in the room have never seen. And the syntax for accessing these devices were different. You would type load to load from the floppy and cload to load from the cassette. And I made the error of trying to access a device that didn't exist and access memory that didn't exist, and the computer froze and I had to reboot, which of course took all of 2 seconds back then. So that was my first memory-related issue. Second, I got to play around with a PDP 1144 a little bit after its useful life. And I was playing around in high school doing Mandelbrot set graphs. And it took forever to do these, what's trivial nowadays, to bring up a Mandelbrot set and graph it. And so I would do it with batch processing. I would give it 12 regions to look at overnight, and it would come back with these beautiful images. And even though I did a homebrewed compression scheme, at one point I did some images which were too complex, and it used up all the memory that was available and all the hard drive, the cassette drive memory, and it crashed overnight. This was a system with 256K of memory, and the cassette drives, I think, had roughly the same amount, and it wasn't so hard to crash it. So you can say my talent for crashing systems isn't that great so far, but I think my crowning achievement came a few years later when I was working for a 3-letter agency that is now a bit infamous in the news. I got my hands on a Cray 2, and I took a problem which was way too large to solve, and I reduced it by several orders of magnitude so I would have a toy problem that I thought would process. And again, true to form, I submitted as a batch and it would go overnight. It turned out I had made a slight error with my order of magnitude calculation, a factor of 1024 here. So I thought I needed half a meg of swap memory, which the Cray was easily capable of. The Cray had about 512 megs of common memory, but it turned out my toy problem needed half a gig of swap memory. Half a terabyte of swap memory. So that, even for a Cray back then, that was impossible. So I brought the whole system down, and there were several other important batches running at the same time. So I came in the morning to some very angry operators. But things have changed a lot since even then. Back then, you've got 1977, you've got 4K of RAM. 1987, the PDP-1144, and this is a little late, had 512K. By 1993, I crashed a Cray with 512 megs. And this is just RAM. When you take external media into account, from tapes to floppies and Bernoulli disks to magnetic hard drives and next generation storage devices, there's been a similar change. And the current state in memory, before flying out here, I went to Best Buy and looked, and it's $30 to $40 per terabyte retail, which is utterly revolutionary if you think about it. We've become numb to what this cheap, almost free memory means to us. We've been so acclimatized to talking about gigabytes and terabytes and petabytes, and everyone's talking about exabytes now, and then it goes yottabytes, something like that, that we no longer have any sense of scale or what this really means. Let me put it this way. Imagine you wanted to record low-quality audiovisual signals at 64 kilobits per second. By today's standards, that's really poor stuff, but it's definitely enough to know what's going on. It's a reasonable quality. For under 60 seconds per minute means that to record this signal, it would take 3.8 megabits per minute. 60 minutes per hour means 230 megabits per hour. Recording constantly for an entire day, that's 5.5 gigabits per day. For a year, you're talking 2 terabits times 100 years. So for a lifetime of audio-visual and low quality, that's 200 terabits, which is about 20 terabytes to record someone's entire audio-visual experience from cradle to grave. In low quality, true, but this is under $1,000. You can strap someone in, give them Google Glass, record everything that they see and hear from the time they were born to the time they die, even when they're sleeping, for under $1,000. If you want high def, do Blu-ray quality, is still within the range of a fairly rich solipsist. 12 petabytes or so per life. And Our optical input is the most information-rich signal that we process. It's the sense that if you look at the map of the brain, that's what we spend the most area, most processing power looking at. You can imagine that we're not too far away from a point where one could record a human's entire sensorium, sight, sound, taste, smell, and touch, and store it. And the whole project would be within reach. You could take every input to the human brain and store it. And it's not that expensive because the memory is just that cheap. And I'll bet you some performance artist is going to do it sooner rather than later. Remember, one of the revolutionary aspects of digital technology is automation. We can gather information continuously and store pretty much everything without the need for human intervention. Just flick on the switch, set everything up, and it goes. And we're automatically creating and gathering large volumes of information, large volumes of data, all the time. This is an image of a particle collision at the LHC near Geneva. I've been lucky enough to visit there. If you ever want to try out a good scientific cafeteria, go to France. It's really good. When two protons collide in the detector, triggers automatically tell a computer to collect data and reconstruct the spray of particles that come from these collisions, and that's a reconstruction. So when one of these collisions happens, within the tiniest fraction of a second, 1.5 megs of data is just collected like that, automatically. And you need not even be in the collection field to generate reams and reams of information. I mean, I'm talking to simulators here. And forgive me for choosing a non-blue waters simulation, but here's something from the Bolshoi simulation. This is probably you guys know more about this than I do, but this is a simulation of large-scale structure of the universe run by NASA. It was done on the Pleiades computer, and the Pleiades computer has 0.5 petabyte of memory, and apparently the snapshots of this simulation that they stored take up about 100 terabytes of disk space stored. And of course, this is just a small fraction of the data that was flowing and changing throughout the course of the simulation. With this much processing and this much storage, you can begin to do things that could never be conceived of before, just through brute force. For example, you could snaffle up all of the world's literature and store it and analyze it. Or like Google, you can also snaffle up all the translated versions of that literature you can get your hands on. Get enough of a corpus, and you can just get a decent translation engine just through brute force. You don't really have to worry about grammar or meaning, just clever enough k-nearest neighbors, and you've got a translation. Just the fact that you've got something close in your corpus is good enough. You can get a pretty decent translation just by virtue of having vast amounts of data at your disposal. Another example that's going on right now, 23andMe. If you get enough genomes of people willing to share their disease profiles, just through brute force, you can find genetic associations for diseases. In this case, we're talking about Parkinson's. And this is a huge change in the landscape. Brute force is actually becoming elegant. And in some ways, this is the real digital divide. This is the real digital revolution, and we're going through it right now. A few years ago, we were living in a world where we were starving for information, that we didn't have a lot of data at our fingertips. We didn't have access to a lot of information from the present, much less from the past. Now, we've got almost unlimited capacity to capture information, generate it, and store it indefinitely. We've moved from the era of information famine to one of information surfeit. In its way, this is as revolutionary as the change from prehistory to history. Humanity's very relationship to information is being transformed. It also changes the fundamental process of information gathering. We now have access to so much information, it doesn't make sense to keep it all. Remember that image of a particle at the LHC? I said that each collision produced about 1.5 megs of data. What I didn't tell you was that there are about 40 million collisions per second. So this is 60 terabytes per second being generated. So you can't store all that. Even if they were the NSA, and they might be able to store most of it, they wouldn't use even a fraction of it because not all the collisions are useful, that they're off-center, they're kind of far out, they're not, I guess you don't have rapidity issues, but you have messy data that just aren't usable. The really nice collisions in the center of your machine where you can reconstruct all the data, all the particle tracks, are in the minority. So what they have is a series of triggers that tell the machine whether it is nice enough and worth keeping. So the first set of triggers, acting almost reflexively, throws out 99.9% of the data, bringing the yield down to a more manageable 40,000 events per second. From there, a second trigger brings it down to 1 kilohertz, tossing out 97% of the remainder. And that brings it down to the speed that software can handle easily. And the computer then throws out another 80% of what's left. At the end, that's still 300 megs per second, a couple of petabytes a day. The art here is not about gathering data, but tossing it out, figuring out how to discard data in an intelligent manner, filtering what you want to see from what you don't. Only one collision in a few 100,000 ever gets through all of these layers of filtering to the point where a scientist actually looks at the data, even indirectly. That's what life is like in the age of information surfeit. You already live there, even if you're not intimately aware of it. This is an estimate performed by Kaspersky Labs about what proportion of last year's email traffic was spam. We can quibble over numbers, but generally speaking, 180 billion email messages per day, the majority, probably 70% or more, is spam. And the majority of that never reaches your inbox because it's automatically filtered out by servers. The vast majority of spam is written by machines, for machines, and never reaches human eyes. And it's not just the machines that are affected by this deluge of uselessness. The last time you went to a big tourist spot, were you struck by the number of people with tiny video cameras recording their entire visit in real time? I always wonder who goes back through these recordings to relive their vacations, their entire visit in real time. Well, no doubt this is about to get even more common. With the advent of Google Glass or the shiny new video toy that's just over the horizon, the number of people with real-time records of their comings and goings will go up tremendously. For these people, it's just a fact that they won't be able to go through even a small fraction of what they record, because real-time memories are just that. They take as much time to retrieve as they do to gather in the first place. If we had perfect recall over our past, we would be stuck reliving them, unable to live life so long as we were being consumed by our memories. About 3/4 of a century ago, Argentinian writer Jorge Luis Borges imagined what it would be like to have total recall, and to be able to relive each memory as clearly and in as much detail as if we were living it the first time around. It's a vision of hell. The protagonist, Ireneo Funes, was trapped in his own brain, paralyzed by his memories. He could do nothing to escape it. Like a good computer scientist, he considered compression. But even lossy compression he realized wouldn't do the trick. He determined to reduce all of his past experience to some 70,000 recollections, which he would later define numerically. Two considerations dissuaded him: the thought that the task was interminable and the thought that it was useless. He knew that at the hour of his death, he would scarcely have finished classifying even the memories of his childhood. As a result, Funes was stuck, incapable of thought, because he was drowning in his perfect memory. Without effort, he had learned English, French, Portuguese, Latin. I suspect, nevertheless, that he was not very capable of thought. To think is to forget a difference, to generalize, to abstract. In the overly replete world of Funes, there were nothing but details, almost contiguous details. The moment that we, as a species, finally have the memory to store our every thought, etch our every experience into a digital medium, it'll be hard to avoid slipping into a Borgesian nightmare where we are engulfed by our own mental refuse. This is perhaps the most monumental change of the digital revolution. Our knowledge is now being limited not only by our ability to gather information and to remember it, but also by our wisdom about when to ignore information and when to forget. This is an essential truth of the digital revolution. Power no longer resides mostly with those who gather and create and store data. It's now passing into the hands of those who are good at filtering the data, sorting it, and finding it. This is how you build empires. You search and you sort and you filter. People depend upon you to search and sort and filter, and you automatically gather information on how people search and sort and filter and use that to manipulate what they see and what they don't. This manipulation is already happening. Whether it's Google or Bing or Google News or Amazon.com or whatever service you're using to find something you want, you're being steered in ways that aren't entirely benign. For example, if you do a Google search, your results are adapted to suit you. This is a slide from a talk given by Eli Parissier, the author of The Filter Bubble. He asked some friends during the height of the Egyptian revolution, the protests, to Google Egypt and see what they got out. Friend 1, Scott, had results that were full of references to the protests. Friend 2, Daniel, was missing results on the protests, but had lots of information about travel. These search results were based upon reams of information that Google had about these people's prior searches. If a filtering algorithm figures out that you're not interested in hearing about protests, you'll be spared the unpleasant news. Your online behavior is dictating what news you're exposed to, what data you're being served. In a very real sense, you are controlling which elements of the outside world you see and which you don't. This is welcome news in many ways. We have all have limited time to read, watch TV, listen to the news, and we can't waste our entire day searching for information on the internet, and this information is becoming a flood. The better the media outlets and search engines are at giving us the information and news that we want, the more efficiently we use our time. But at the same time, there's a very big downside. We tend to shy away from ideas, from information, from data that challenges our assumptions, that erodes our preconceptions. Getting rid of our wrong ideas is a painful and difficult process. Yes, yet it's that very process that makes data truly useful. This is a graph from Shannon's famous 1948 paper. It shows the entropy, or maximum information, contained in a stream of symbols against the predictability of that stream of symbols. And the point of this graph is that we get information when the stream of symbols is unpredictable. We get information when we're unable to predict what we're going to see next, at least to some extent. We get zero information when we are able to predict with perfect fidelity what the message is. Information resides in the spaces where we're uncertain, where we're unsure, where we don't know what's coming next. And here's something of a corollary. A fact becomes information when it challenges our assumptions. Those challenges are the raw material that forces our ideas to evolve, our taste to change, our minds to grow. The more power we have over the data that comes in, the better able we are to shelter ourselves from uncomfortable truths, from facts that challenge our preconceptions and misperceptions. With news and data that is tailored to our prejudices, we deprive ourselves of true information. We wind up wallowing in our own false ideas, reflected back at us by the media. The news is ceasing to be a window upon the world. It is becoming a mirror that allows us only to gaze at our own beliefs. And to do this, the measure of success is not gathering new information, but filtering it, sorting it, and processing it in clever ways. The primary gathering of data is secondary. The smart presentation of data is primary. If you do the latter well, you can completely ignore the former. Not long ago, a website known as The Verge ran a very decent long-form piece on the decline of the American arcade. It got quite a bit of attention. Nostalgia pieces tend to do well nowadays. But people who Googled to find the piece, even if they used the exact title in quotes, even if they used phrases from the first paragraph in quotation marks, wouldn't be steered to The Verge's website by Google. The first Google result was uniformly to this: the Huffington Post. It was just a cut and paste job of the first paragraph. But the filtering algorithm thought that Huffington Post was the source of this story and The Verge was the copy. And this happened partially because Huffington Post is big and Verge is small, but it also happened because the Huffington Post webmasters knew to put canonical link in their HTML code, which signaled the search engine that this was the real copy and The Verge was a fake. Huffington Post has made its fortune on this kind of chicanery. Repackaging other people's stories in the right way will generate traffic without any need to generate your own. And this is one of the big pitfalls of big data. Our dependence on filtration means that there's a machine layer that's attempting to determine the meaning on some level, to tell us the quality of a result. And that process is fallible and gameable. With large amounts of data, there are large numbers of false trails. Machines can pull out correlations in large data sets automatically, but they can't tell us whether they have any meaning whatsoever. This actually comes from one of my new favorite blogs, which talks about false correlations. Large studies, like the Nurses' Health Study or the Framingham Heart Study, are mined and produce results which seem not to make sense. And all of you working in simulation know that your model is only as good as your underlying knowledge. If you're missing something fundamental, your model won't work as fancy as it is. Garbage in, garbage out. This is the output of one of several types of simulations that fusion researchers at Livermore produce. Anyone from Livermore here? Good. It looks at the implosion of a pellet of deuterium and tritium. And you can see the effects for those of you who like fluids. These are Rayleigh-Taylor instabilities on the surface as the pellet is violently compressed by X-ray radiation from the whole realm. Simulations like these proved to Livermore scientists' satisfaction that their new multi-billion-dollar laser, NIF, would ignite a fusion reaction in the pellet. Did it? Not even close. The line 1800 kilojoules is actually the ignition criterion, which they touted for many years. If you remember, just in February, end of February, there was a big to-do about breakthrough in fusion at NIF. That little blue wedge in the lower right-hand corner is their breakthrough, compared to ignition, which they initially promised and continuously promised, even as they knew their machine was many orders of magnitude, and they're still 2 orders of magnitude away from ignition, and they're not going to get it with this device, at least to all appearances. The simulations were way off, as they had been for years. Here these scientists are in 1978, many of the same scientists. These are John Nichols and who's the other one? Can't remember who the other. Pardon me? It is Emmett. Yes, John Emmett. Bragging in 1978 about their, quote, oracular Lasnex code, unquote, which was going to indicate that their new machine, Nova, was going to reach ignition by 1990 at the latest. Here we are 35 years later, and they're making exactly the same mistake. Simulations are a wonderful tool, as you all know, but there are good ones and there are bad ones. There are codes that predict precisely what you'll see in an experiment, and there are ones that are way off. And this is part of the reason I was so encouraged when you were talking about the increase in simulations that are actually folding in real-time data, because that's a great way of validating. Big data and big simulations are just as vulnerable to BS as other kinds of research. And in the case of Livermore, they used their codes not so much to figure out the future as much as they did to generate support for their project. And this is another danger of big data. It can be very impressive and very hard to validate, meaning that it is virtually unfalsifiable. This is great if all you want are peer-reviewed publications for your resume. It's also great if you're a peer-reviewed journal looking for plausible but meaningless papers to publish. This is a fairly important paper in the CS community. I suspect that many of you know it, but it's not important for any of the normal reasons. I'll read the abstract quickly. Many physicists would agree that had it not been for congestion control, the evaluation of web browsers might never have occurred. In fact, few hackers worldwide would disagree with the essential unification of voice over IP and public-private key pair. In order to solve this riddle, we confirm that SMPs can be made stochastic, cacheable, and interposable. This is a paper generated by a script. And this is Reuter. It's very famous. Reuter was accepted to a conference, a peer-reviewed conference. It passed the peer review process, or the peer review process, even though it's utter nonsense. It is easy to dismiss this paper as an anomaly, but if you look carefully, you can find script-generated papers all over the peer-reviewed literature. Just a couple of months ago, Elsevier and IEEE pulled more than 100 papers that had been written by the exact same script that had produced Reuter many years ago. And this is just a tip of the iceberg. There are plenty more out there still waiting to be found. I just, before the conference, looked for a few. Here's one. CLART, Trainable Concurrent Modalities. Large-scale configurations in SCSI disks have garnered limited interest from both mathematicians and physicists in the last several years. In this paper, we disconfirm the deployment of public-private key pairs. CLART, our new methodology for multimodal theory, is the solution to all of these obstacles. Here's another one, DOC-based active networks. The steganography method to architecture is defined not only by the development of Smalltalk, but also by the unproven need for 2-bit architectures. In this work, we disprove not only the study of vacuum tubes, which embodies the unproven principles of networking. DOC, our new heuristic for homogeneous configurations, is the solution to all of these obstacles. Notice any patterns? This isn't a function of big data, but for me, it encapsulates perhaps the danger of the era of information surfeit. We have a big increase in signal, but we have an even bigger increase in noise. It takes ever more effort to distinguish the two, to the point where we're partially dependent on machines to do the distinguishing for us. And at the same time, we humans seem less willing, less capable of doing the validation, the checking, the quality control that can't be done by machines. The result is that we generate a tremendous number of seemingly important advances when an increasing proportion of them are worthless. It's amazing how quickly digital information has transformed us from a society with information famine to one trying to figure out the consequences of information surfeit. It has taken less than a generation. Now we're in a world where everything we do, where everything we produce, is adding to the surfeit. And unless we're careful, we will drown in our own mediocrity. Borges put it succinctly, describing his protagonist, a vision of his protagonist for the first time. Then it was that I saw the face of the voice which had spoken all through the night. Ireneo was 19 years old. He seemed as monumental as bronze, more ancient than Egypt, anterior to the prophecies and the pyramids. It occurred to me that each one of my words, each one of my gestures, would live on as an implacable memory. I was benumbed by the fear of multiplying superfluous gestures. Thank you.
We have time for some questions. Does anybody have a question? You have to have questions.
So, can computer programs detect computer-generated papers? Yes, if you're smart about it. Especially if you get the script itself. You could. The way I detected it actually is there are some key trigraphs, digraphs that appear in these papers over and over again. They're clearly drawing from certain buzzwords, and if you search for multiple buzzwords or multiple ones of these trigraphs superimposed, you're going to get these hits very easily. And in theory, yes, you can. If you know the algorithm for generating these papers, you can create an algorithm for detecting these papers. But then what you do is you trigger an arms race. And that's exactly what's going on with spam. That back in about a decade ago, you might have remembered that some of the spam had these really strange prose poem sets of words at the bottom of your spam. And this was an attempt to defeat Bayesian filtering, because you had this new weapon come out, Bayesian filtering, that initially was tuning to certain words which were and weren't in spam. And the spam algorithms tried to defeat them by adding words which weren't in spam. So they would take from a different corpus to try to defeat the Bayesian filters. And it worked for a while, but then you trained your Bayesian filters in a different way, and the spam evolved in a different way. So you just get kind of a Red Queen situation where you just have to keep running to stay still. So yes, algorithms can help us, but at best, it's going to keep you from getting worse. And generally, in Red Queen situations, you lose over time rather than win.
I'm glad you brought up spam again and filtering it. Why hasn't another solution other than filtering it, just eliminating it, come about? Do you have some insight into that?
I'm not sure I have much more insight than you guys all have. It seems that the other processes, that the other ways of doing it other than filtration are so burdensome. Again, about 10 years ago, whitelisting became popular, that there was a service out there that you could force your friends to sign up or pass a CAPTCHA before sending you an email for the first time. It never caught on because it's burdensome. And as with everything else, I mean, the security and convenience are working against each other. And I think that if we want to have an open society where everyone can email each other without putting too many burdens to prove that you're actually human and have something important to say, you've got that balance. And I don't think anyone struck a very good one. Yeah, I mean, you can say block out areas of Western Africa and Russia and have extra burdens upon them. I mean, it's possible that that would work. Of course, it would be burden upon the legitimate traffic coming from there. It would also mean that the smart spammers just have their botnets operate from somewhere else. Because a lot of these are remote. You have a botnet, you can set it up in Des Moines. And you have 20% of the world's spam coming from Des Moines for a week, and then it moves somewhere else.
Are most of these computer-generated papers motivated similar to Alan Sokal's to highlight problems in the peer review process, or are they just done for the lulz?
I think both. I think both. I believe the initial Reuter paper was aimed at someone who was criticized for running essentially predatory journals and conference proceedings. And you all have probably encountered these predatory journals and conference proceedings. These are places where they will accept everything for a fee, and you come and present, and no one cares about it, no one really checks it. There's a whole, Jeffrey Bial, a librarian and expert in peer review, has an entire list of what are called predatory open access journals. So yes, a lot of these fake papers, and I think Science Magazine in the past year actually did exactly that. They created a bunch of fake biology papers, submitted it, saw what got through, and almost all of it got through. But some of it is just people having fun, submitting it randomly, see whether it could get in, and often it does.
I was wondering, you mentioned people, this horrible world where you recall all your memories. There are actual individuals who have that kind of memory recall. Are you aware of that? Did you research that when you were doing that?
I've looked, I mean, I don't know all that much about eidetic memories, but they do exist. But they're usually, from what I understand, focused in a certain area. That, for example, you have visual recalls of still images, or you have perfect auditory recall for certain passages. But I don't think it extends to a Funes. But again, I'm not an expert. If there are Funes people out there, I think it would be fascinating to see how they actually cope with the filtration that they have to do.
So the real question is, does this work for generating proposals too?
Do we have one more question? Well, Christina?
So we're producing more and more data, and we know that in our own project. At a certain moment, we do have to do this filtering ourselves and decide what is worth keeping for a longer time. It all comes at a cost. How are we making those decisions? How can we make those decisions in a better way?
That's a very broad question. I think, well, I can say is certain people, when I'm complaining about lack of filtration, it's actually not universal, obviously, that there are journals that are doing very good work at filtering, but even with Nature and Science and top-tier journals, you get filtration errors. And I think that's true with any system that's generating large amounts of data. With CERN, for example, one of the questions I asked many years ago was, how do you know your triggers are set up correctly? Could it be that a signal that you don't know is being cut out in one of those filters? And you might be missing a completely anomalous signal that you didn't plan for in your initial thoughts. And they said, yes, that's a worry. But we try to be as inclusive as we can be and not cut signal. We make our cuts so that the likelihood of that is very small, but there's always that risk. So I think even if you're really good at it, there's always a risk. How can you do it better? I don't know. I mean, in some ways, Google is doing it very, very well. They're tailoring stuff to your preferences. They have an algorithm that beats everyone else's at taking large amounts of data, filtering it, getting what the consumer wants and needs, but it also has its drawbacks. So maybe it's not a matter of doing it better as much as understanding that it's a double-edged sword and positioning yourself so that the downside isn't as bad as the gain from the upside. And I think with simulations, I mean, always keeping in mind that this validation is crucial. I can't give advice to the choir here about simulations, but I think it's really important to keep in mind that every scientific result that has meaning is falsifiable in some sense, and if it can't be falsified, then perhaps you have to question whether it's useful, and aim your work towards something that at least is falsifiable in small ways.
So your talk brought a few things to mind. The first one is we're going to be very careful about giving you accounts on Blue Waters because of your history of crashing machines. But the second one is I have to call upon the community here, particularly those that work in cosmology and things, to get a slide that is a Blue Waters related slide for Charles's presentation. So I think, Brian, you have a job to do in the next 10 minutes to get some slides up here. So, but I would like to thank you very much for a thought-provoking and very different view of things, and appreciate your trials and tribulations getting here, and hope you can stay around a little bit to interact with the folks here. So thank you.